morning all. I am Dr. Vandana Yadav and today we are going to discuss stereochemistry. This is the very important topic for graduate and undergraduate student. I hope you all will get enriched after this lecture. Stereochemistry is the branch of chemistry which deals with the structure of molecules in three-dimensional, and we all know that the concept of stereochemistry starts with the study of isomers. So let's discuss isomers. Isomer word itself is made from two words, iso which means similar and mer mean parts. So same parts are categorized as isomers. So we can define it as compound molecular formula but different structural formula. Let's have an example. We have C2H6O. This is the molecular formula, and with this same molecular formula, the two compounds, alcohol and ether, exists. Both are having different functional group. One is the alcohol which is having entirely different properties, and another one is dimethyl ether. So the existence of these two separate compounds with the same molecular formula is called isomerism. So we can define isomerism is the existence of these two different compounds with the same molecular formula is called isomerism. Coming on to the types of isomerism we encounter in organic chemistry. So let's have a look at the types of isomers. Types of isomers. So they are further subdivided into constitutional isomers and stereoisomers. As the name suggests, constitutional means related to the constitution and stereo means related to their arrangement. So on this basis, they are further subdivided into three categories: chain isomers, position isomers and functional isomers. And the stereo are further divided into optical isomers and geometrical isomers. So we are clear with the classification of isomers: constitutional, stereo. Constitutional are further subdivided into chain, position and functional. So let's have the look of each of the category of isomers. Chain, as the name suggests, the compound will be having same molecular formula but the structure of chain will be different. For example, if I have C4H10, you all know about butane, but if I can draw it in the form of a linear structure, and I can also arrange structure. The constituents are same, but you can see the chain is linear and here it is branched. So these two are related to each other by chain isomerism. Coming on to the position isomerism, as the name suggests, position. So the position of the functional group will be different in the two structure. For example, I consider one butene and I have two butene. Both are having same number of carbon and hydrogen, but as you see, the position of double bond in the first structure is at first carbon, however the position of that is second carbon in the compound. So, the relation between these two are that they are positional isomers of each other. Now, functional isomer. Functional isomers, if I draw the structure of C2H6O, molecular formula is C2H6O. Now, it can be either a alcoholic functional group or it can be either a dimethyl ether. So, they are having C2H6O composition, but the functional group are entirely different, and based on this they have different physical and chemical properties, and they both exist in nature. So, we can say that constitutional isomers are basically the difference between their structure, their functional group, or the placement of that functional group in the carbon chain. So, this is constitutional isomer: chain, position and functional. Now, we are going to start with stereoisomers. As I already told you that stereo means something related to arrangement. So, before discussing stereoisomers, so let us discuss the concept behind the discovery of stereochemistry. Have you ever wondered that why we are not able to wear our right shoes in our left foot? Or have you ever tried to wear your right glove in your left hand? Do you feel the pain? Surely you must be. Why? Have you ever thought of this concept that why we are not able to wear your right shoe in your left foot? This concept is called handedness. Handedness means that if I see the mirror image of my left hand in the mirror, what I see? I do not see the left hand, I see the right hand. So, the mirror image of my left hand is different, it gives the structure of right hand. So, this is called handedness, and the object which show handedness are given a name which is called chiral. Chiral give rise to chirality. So, the handedness is basically having chiral nature. However, if you try to superimpose left hand on your right hand, you cannot do so. Why? Because one structure is having left handedness, other one is having right handedness. So, that is why the term chirality or chiral came into existence. But we can say objects are not only chiral, but the molecules are also chiral. But there are other molecules also which do not show such behavior. For example, so some of the objects as we encounter in our daily life are not the same or not having handedness. Like you can see the chairs. If I see the mirror image of this chair, it will be this chair, no difference in them. And if I want to stack them, they are stacked one over the other. That means they are not having handedness, and hence they are categorized as achiral. So, any object which is same as its mirror image is called achiral. So, coming back to chiral nature. So, we have seen the objects in our daily life which are chiral, but we also encounter with molecules that are chiral, and the chirality in molecules arises due to asymmetric carbon. So, asymmetric carbon. Now, let us discuss what is asymmetric carbon. You all know symmetry. Now, asymmetry means, as you all know, that carbon is having valency of 4 and it can form 4 covalent bond. Now, suppose it forms 4 covalent bond with 4 different types of atom, then I will categorize this carbon as asymmetric carbon. So, a carbon with 4 different atoms attached to it becomes the asymmetric carbon, chirality arises. Now, chirality and chiral, it is the two concepts. So, you have to understand, if I am talking about chiral atom, then I am talking about this carbon which is attached to 4 different atoms, and when I am talking about chirality, then we are talking about certain important features. So, let us discuss those features which causes chirality in our organic molecules. Chirality or chiral nature give rise to stereoisomers. Now, you will say, what are stereoisomers? We have studied isomers, but what are stereoisomers? So, we can first discuss stereoisomers. The structures which are having same atoms, but the connectivity of the atom is different in a 3-dimensional space. They are called stereoisomers, and the existence of these type of structure give rise to stereoisomerism, and stereoisomers are due to the presence of chiral carbon or chiral atom. Let us classify stereoisomers. So, stereoisomers can be optical isomers, optical as the name suggests, something related to light, optical isomers and geometrical isomers. So, today we are going to focus on optical isomers, subdivided as enantiomers and diastereomers, and in some cases we also encounter meso compounds. So, we are going to discuss optical isomers in detail. So, I am going to explain this optical isomerism with the help of one example which you all are aware about. It is tartaric acid. So, you all must be knowing tartaric acid. Tartaric acid is a compound which is having 2 carbon which are chiral in nature. So, chirality we have studied. So, a carbon which is attached to 4 different atoms becomes a chiral center. So, this point and this point, these are the carbon, and they are attached to 4 different groups. So, this becomes the first chiral carbon and this becomes the second chiral carbon, and this is the of tartaric acid. To draw the mirror image of this structure, I keep a mirror in front of this and I ask you to draw the mirror image of this structure. So, the mirror image will be something like this. Now, try to superimpose them. You all know superimpose. If I ask you to superimpose your left hand with your right hand, if this way I can do, but this is superimposes, these are 2 structures, and if I try to superimpose them, then the impression of thumb is one is at left hand side and another one is right hand side. So is the case with this structure. If I try to put it this way, I will see the OH here is in left direction, however, in the lower one it is in right direction. So, this is the second structure of tartaric acid, and the 2 structure of the same compound which are non-superimposable mirror images, they are categorized as enantiomers. So, the relation is that 2 structure of the same compound which are non-superimposable mirror images, they are categorized as enantiomers. Now, we can have the third structure of tartaric acid. What will be that? if I place both the OH on the same side, then it becomes the third structure and entirely different from the two which we have already discussed. So, this structure is having both the OH on the same side, and if I try to draw the mirror image of this structure, then OH in this structure will come to left hand side. So, I can name them third structure of tartaric acid and fourth structure of tartaric acid. So, these two are another two structure of the same compound. What compound? So, total 4 structures are there, but there must be some relation between all the 4 structures. So, I told you that 2 structures which are non-superimposable mirror images of each other are called enantiomers. So, I can categorize 1 and 2 structure as enantiomers, and similarly third and fourth structure can also be categorized as enantiomer. So, third and fourth, they are also enantiomer. But have you ever thought that the 4 structures are of the same compound? So, there must be some relation between 1 and 3, or there can be some relation between 1 and 4. Yes, there is. So, if one structure is not the mirror image of the another structure of the same compound, then a new term is derived which is called distereomers. So, the 2 structures of the same compound which are not the mirror images, you have to remember, not the mirror images, they are called distereomers, and here we have 1 and 2, 1 and 3, 1 and 4, and 2 and 3 and 3 and 4. So, these are a set of distereomers, pair of distereomers existing in case of tartaric acid. So, now I think you are clear with the concept of enantiomers and distereomers. However, if you observe this structure, and if I draw an imaginary line in the middle of this structure, so you can see is the mirror image of another half, or I can say that through this imaginary line I can divide this molecule into 2 equal halves, and here the third term comes, that such structures which are having plane of symmetry, they are called mesocompounds. Mesocompounds arises only in the case of molecules which are having 2 carbon which are similar in nature. So, we must understand how we are going to study the optical activity. The optical activity is studied by passing the plane polarized light. Now, you will say, what is plane polarized light? Plane polarized light, or we call it as PPL. It is the unidirectional light. Unidirectional means if I take a multi-directional light normally, which is vibrating in all the direction, a normal light, if it is passed through some prism, it becomes unidirectional. So, if any compound rotate means this is the plane polarized light, right, or it can be rotated towards left. So, right or left. So, any compound when passed through plane polarized light rotates it either towards left or toward right, carries optical activity. And if any compound is not rotating it in any direction, then it is optically inactive. So, let us have a look at the structure 1. at the structure 2, 3 and 4. If for example, structure 1 rotates the plane polarized light towards right hand side, then being the mirror image, this structure will rotate towards the left hand side. So, I can categorize that enantiomers are optically active because they are rotating plane polarized light either towards left or towards right. So, they are activity. So, I can say that enantiomers are optically active compounds. But in this structure, I told you that one half of the structure is the mirror image of another half, and here we have studied that if one is the mirror image and another is the main structure, then they rotate plane polarized light in opposite direction. So, we can categorize that any structure which is having a plane of symmetry is optically inactive. Why it is optically inactive? If one half of the structure will rotate the molecule plane polarized light in the right hand side, then another will rotate it in left hand side. So, if I rotate half of the structure rotated it like this, another half will rotate it like this. So, overall rotation becomes 0 and plane polarized light comes back to its original position. So, then we can categorize that these structures are optically inactive. So, with all this discussion, I can summarize the difference between enantiomers, diastereomers and meso compounds. So, enantiomers, let us have a look at the important points of enantiomers and diastereomers. So, what I can say is enantiomers we have studied. Enantiomers are the two structures of the same compound which are non-superimposable mirror images of each other. And diastereomers are images of each other. Second point of difference, I told you enantiomers are optically active, only direction of rotation is different. Though extent of rotation is same, but direction of rotation is different. If one is rotating it in right hand side 25 degree, other will rotate it in left hand side 25 degree. Coming on to diastereomers, diastereomers may or may not be optically active, may not be optically active. So, as the structure suggests, enantiomers are having identical physical and chemical properties like melting point, boiling point, because they are mirror images of each other. So, the left hand and right hand are having the same properties. Diastereomers are having identical physical properties, but they can have different chemical properties. So, this was the summary of enantiomers and diastereomers. So, these are the two type of optical isomers, and meso compounds are only encountered when we have two or more symmetric, asymmetric molecule, or I can say meso compound due to presence of symmetry in a molecule, and in all meso compounds are optically inactive due to the presence of plane of symmetry. So, with this discussion we can derive certain conditions which are necessary for the presence of optical activity. Certain conditions necessary for optical activity. Number one is, as you have studied, number one is presence of asymmetric carbon. Number two, non-superimposable mirror images. And the last one is absence of any symmetry element, absence of any symmetry element, because if there is symmetry element it will become meso compound and it will become optically inactive. So, the optical activity is studied with the help of instrument called polarimeter, and we study the specific rotation of that particular molecule. Now, coming on to some application of optical isomers, or you can say the application of stereochemistry is in biological system or our body, medicinal chemistry. As you see, a particular lock has a particular key. So, similarly in our body we have receptor can accept only one of the structure or one of the enantiomer. So, therefore, our drugs or you can say our medicines are made from one type of molecule. For example, you must have encountered with citrazine. Earlier doctor used to prescribe citrazine, but today it has been changed to LCZ, it is levocitrazine. So, levo word indicates that the structure which rotates the molecule towards the left hand side is used as a drug, because right hand side does not accept our receptor, or we can say does not fit into our receptor. So, the stereochemistry is having a very wide application in medicinal chemistry. So, today we discussed the concept of isomerism and optical isomerism. I hope you all get enriched by this lecture, and in next lecture we will be discussing geometrical isomers and some more examples of optical isomers. Thank you.